All right, for today, let's take a look at the formation of triple bonds. You'll see it on this slide here, but again, I want to show it to you my own way because I don't like the way the book does this. So far, we've looked at forming normal single bonds where you just, share the electrons. Sometimes we saw that you needed to form double bonds where you didn't have enough to go around. So today we'll look at forming triple bonds. Let's, as a reminder, I guess, look at the diatomic oxygen molecule. Remember, each oxygen has 6 electrons, so that's 12. So 2, 4, 6, those are ugly dots, 8, that oxygen has 8. Now 10, 12, this oxygen comes up short, so we had to steal, say, these 2 electrons and shift them in to make a double bond. Again, notice everybody still has 8 electrons, 2, 4, 6, 8, and now 2, 4, 6, 8 for that one. So forming a double bond allows you to act like you have more electrons than you really do and make up for coming up short. Today let's look at a situation where we come up even more short. Let's do the diatomic nitrogen molecule, N2. Now, again, obviously it's nitrogen bonded to nitrogen. Each nitrogen comes in with 5 electrons, S2P3. 2 plus 3 is 5 electrons. Another 5 for the other. That gives you 10 electrons to work with. Okay, so form a bond. That's 2, 4, 6, 8, 10. I've used all 10 electrons, and this nitrogen is still short quite a bit. The nitrogen on the left has 2, 4, 6, 8 electrons, but the nitrogen on the right only has 2, 4. So what do? Well, we can take one pair of electrons away from here and make a double bond. Now again, the nitrogen on the left has 2, 4, 6, 8. That's still fine. The nitrogen on the right, 2, 4, 6. Well, before it only had 4, now it has 6. It's getting better. But we're still not there. What do? Let's take another pair away. Again, it wouldn't matter which pairs you take away and make another bond. I like to keep it symmetric on either side there, but it really wouldn't matter. The dots could be above, below, whatever, as long as they're paired up. You couldn't have one above, one below, or something like that. Now, notice again, the nitrogen on the left didn't lose anything. We just took 2 electrons and shifted them over here. It still has 2, 4, 6, 8 electrons. But now the nitrogen on the right has 2, 4, 6, 8 electrons also. We give everybody their full shell at the cost of forming a triple bond. You got 3 complete electron pairs holding these atoms together. Okay? By the way, yeah, to make the numbers work out, we have to do this, but do we have any evidence for these things? Well, among other things, yeah. Like, for example, if you take, say, chlorine to chlorine, that's a single bond in there. Well, actually, let's do fluorine to fluorine. I'll come down below. That way I stay in the same row. A fluorine to fluorine single bond has a certain length to it, whatever number of picometers between the 2 atoms. If we go to the atom right next door, which is oxygen, oxygen to oxygen double bond, notice the bond length I tried to draw it a little shorter. The bond here between the fluorines is longer, right? So a double bond is shorter than a single bond. When you measure the length of the bond for the fluorines, you get whatever 100 picometers. If you do it for oxygen, you get a smaller number of picometers. So it's a shorter bond. And a triple bond is even shorter yet. Obviously, when we drew Lewis structures, we don't draw them their actual length. But single bonds are long, double bonds are short, triple bonds are even shorter yet. So these things are measurable. The reason why, by the way, is because there's more electrons. Remember, each atom has a nucleus with positive charges. These negative electrons in the bond are pulling those positive charges toward each other. You got 1 pair of electrons in here pulling on the positive charges. Here you got 2 pairs of electrons pulling on the positive charges. There's twice as much negative charge pulling them in. Here there's 3 times as much negative charge pulling them in. So as you go to single, double, triple bonds, the bonds get shorter and shorter. Okay? People sometimes ask, can you get quadruple bonds? It's extremely rare. It's not something you have to worry about here. But occasionally weird things happen. So anyway, that's that. Now, Let's look at an example molecule that you'll have a triple bond in. Let's do the hydrocyanic acid molecule, HCN. Okay, so you got, well, it's linear just the way you see it. It's a hydrogen hooked up to a carbon hooked up to a nitrogen. By the way, when I give you these things on the homework, like I did yesterday, usually the atom that there's only one of goes in the middle. If in a case like this it's not clear, either I'll give it to you in the order they're hooked up, or I'll give you a little parentheses note saying, hey, put this guy in the middle, or some such. But usually it's pretty obvious. Now, let's add up our electrons. Nitrogen, I'm going to start from right to left. Nitrogen has 5. Carbon, S2P2, can't find my cursor as usual. Carbon, S2P2 has 4. And then hydrogen has 1. So that gives you 10 electrons to work with. All right, let's make our bonds. 2, 4. Okay, I used 4 of my electrons. Now, hydrogen, remember, doesn't need any more. It only needs 2. It got its bond. That's all it gets. Hydrogen will never get lone pairs. If you have lone pairs on hydrogen, you're doing something wrong. So, all right, let's do the carbon and the nitrogen. Remember, it's usually best to save the central atom for last, so you got room to mess around. So I used 4 already. 6, 8, 10. Oops. Now I gave nitrogen its octet. 2, 4, 6, 8. I used all my electrons. Carbon only has 2, 4. So carbon's coming up really short here. So again, what do? Take some of these electrons, erase them, make a double bond. Nitrogen still has 2, 4, 6, 8. It's good. Carbon has 2, 4, 6. It's still not good. So what do? Make another bond. Erase those electrons. Make a triple bond. Now carbon has 2, 4, 6, 8. It's got its full shell. Everyone's happy. Okay. Now, again, in this case, notice I didn't have to worry about messing with the hydrogen. If that had been like a sulfur or something, you would have had to worry about playing with that too. But that's it. Just like before, if you have an ion, you gain and lose electrons as you have positive and negative charges. Positive charges lose electrons, negative charges gain electrons. And you did some of that yesterday. So if I had been doing the cyanide ion, Cn negative, I would have gained an extra electron because of that negative charge. Okay, let me leave it as that. It's a really short lesson for today because all I had to do was show you how to do triple bonds. Tonight's homework is going to be just to do the same thing as last night. I'll give you a bunch of different compounds. They can be single bonds, double bonds, triple bonds, all throughout the whole thing. And you just build the Lewis structures properly. I think tomorrow maybe I'll show you resonance, and from there we'll pause and talk about taking a quiz on all this stuff. All right, that's it for today.